Welcome back, everyone. Get ready because today we are preparing to explore one of the most advanced engineering machines ever built by human hands. Picture this. You're looking out over a vast ocean at sunrise, right? The gentle waves are just shimmering under the golden light. But as we begin our descent in today's explainer, that warm sunlight quickly fades into a deep, heavy, pitch blue darkness. Far below the surface lies a machine that can travel completely silently for months on end in total isolation. Today, we are going to unpack exactly how a modern submarine works. Here is the game plan for our mission today. We'll start with the anatomy of a submarine, then dive into the physics of how they actually submerge and how they navigate the deep dark. After that, we'll cover power and life support, surviving extreme ocean pressure, and finally, ascending back to the surface. Let's get right to it. Okay, let's dive into Section 1, Anatomy of a Submarine, peeling back the hull. To really understand how this vessel survives, we've got to realize that a submarine is much, much more than just a hollowed-out steel tube. If we could somehow make the outer hull transparent, you'd immediately spot these core internal systems. I mean, these are literally the brain and the heart of the vessel. You've got the outer hull giving the sub its sleek hydrodynamic shape, but tucked safely inside that is the pressure hull. That's the incredibly strong inner layer that actually protects the crew. Surrounding those are the ballast tanks, which, as we'll see in a minute, are absolutely crucial for sinking and floating. And then you have your critical operational centers, the control room where the officers command the ship, the reactor room generating all the power, and the battery banks. All these components are specifically designed to keep the crew completely safe while operating in a totally alien environment. Now, wrapping around that core are the crucial external and tactical systems. Up front, you have the sonar system dome, the torpedo room, and the crew quarters packed tightly in. In the back, you've got the mechanical muscle, the propeller, the rudder, and the diving planes. Those diving planes actually act a lot like airplane wings, just, underwater, helping to steer the sub up and down. Finally, we've got the high-pressure air tanks and navigation systems. And the wild thing is, all these components work in perfect tandem. They allow this massive machine to travel silently and seamlessly for months at a time.
Moving right along to Section 2, the physics of diving, descending into the abyss.
So we know what it looks like on the inside, but how do thousands of tons of steel actually submerge? Well, to understand this, we have to go back to a fundamental physics concept. Archimedes' principle states that an object in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. The really crucial takeaway here is that sinking is simply a mechanical tug-of-war between two things, the downward weight of the submarine and the upward buoyant force of the ocean water pushing against it. The secret to winning that tug-of-war lies entirely in those ballast tanks we mentioned earlier. To initiate a dive, the crew opens up the ballast tank valves. The compressed air that was holding the submarine afloat on the surface is allowed to vent out, and heavy seawater rushes in to take its place. Step by step, as water fills those tanks, the overall weight of the submarine gradually increases. Once its total weight becomes heavier than that upward buoyant force, well, the battle shifts. The vessel begins a slow, highly controlled descent beneath the waves. And down we go. Imagine just watching the depth indicator drop in the control room. You pass 20 meters, the light from the surface starts to fade. You pass 100 meters, and the water turns this deep, inky blue. You drop past 300 meters, and finally settle at 500 meters deep. Down here, the water pressure is just immense, and the ocean is entirely 100% devoid of sunlight. Which brings us to Section 3, Navigating the Deep Dark, Sensing Without Seeing. Down at 500 meters, the submarine is cruising silently through complete pitch black darkness, which leads us to a fascinating, kind of terrifying problem. How exactly do you navigate when GPS signals cannot travel through seawater? Think about that for a second. The GPS on your phone works using satellites, but those radio signals instantly die the second they hit the ocean surface. So how on earth does a multi-billion-dollar vessel avoid crashing headfirst into an underwater mountain when they are essentially driving blind? The answer lies in some truly brilliant engineering. Since they can't rely on GPS, officers in the control room monitor holographic displays fed by some highly specialized tools. You've got inertial navigation systems and insanely sensitive gyroscopes that track the submarine's exact movement and rotation from a known starting point. Depth sensors tell them exactly how far down they are, but their true eyes in the dark, that would be sonar, which stands for sound, navigation, and ranging. Since light can't pierce the deep ocean, sound essentially becomes our flashlight. The sonar system sends out pulses of sound waves through the water. These waves travel outward until they hit something. Could be an underwater mountain range, another ship, or even just marine animals. Once the sound wave hits an object, it bounces right off and echoes back to the sub. By listening to exactly how long it takes for those echoes to return, the massive sonar computers in the control room can mathematically paint a highly accurate 3D map of the surrounding terrain. It literally allows the crew to sense the world around them without ever actually seeing it. Let's look at Section 4, Power and Life Support, Surviving in Isolation. Okay, so we're successfully navigating the dark, but while the sub deals with the hostile ocean on the outside, the inside has to be a fully self-sustaining, illuminated environment for the crew. Running all those navigational computers, pushing thousands of tons of steel through the water, and just keeping people alive takes a massive amount of electricity. Modern submarines generally handle this in one of two ways: diesel-electric systems or nuclear reactors. Now, diesel-electric subs are incredibly quiet and very efficient, but they do eventually have to surface or use a snorkel to run their diesel engines and recharge the batteries. Nuclear submarines, on the other hand, they play by a totally different set of rules. Inside a nuclear sub, it's this incredible chain reaction of energy. Tucked away in a heavily shielded compartment, a nuclear reactor generates immense heat. This heat boils water into highly pressurized steam. That steam is forcefully directed to spin these giant turbines. As those massive turbines spin, they drive generators, which produce an absolute abundance of electrical power for the whole ship. Finally, that power runs electric motors to rotate the propeller. It's a beautifully closed-loop system turning nuclear heat into continuous, quiet propulsion without ever needing a single drop of oxygen to burn fuel. But hey, power is only half the battle, right? Human beings actually need to breathe. So advanced life support systems are constantly running in a continuous loop to make surviving in isolation possible. Oxygen generators literally split water molecules apart to create breathable oxygen for the crew. Mind-blowing, right? Meanwhile, CO2 scrubbers actively suck the dangerous carbon dioxide out of the air. Water purification systems desalinate the ocean water so it's perfectly safe to drink, while air filtration systems keep the whole atmosphere clean. Because of this perfectly engineered loop, the crew can eat, sleep, and work for months on end. Section 5. Surviving extreme ocean pressure, the invisible enemy. As peaceful and cozy as it might sound inside that self-sustaining bubble, there is a totally hostile, invisible threat lurking literally inches away from the crew at all times. Hundreds of meters down, the surrounding water exerts enormous pressure. We are talking about the physical weight of the entire ocean above, pushing down and crushing inward against the hull. At these depths, the forces are so extreme that even the thickest steel layers actually flex and compress slightly under the sheer weight of the water. Just let that sink in for a second. To combat this invisible enemy, the submarine relies on some extreme material engineering. The pressure hull, that inner layer we talked about earlier, isn't just a basic metal pipe. It's forged from ultra-high-strength steel and sometimes specialized titanium alloys designed to withstand unimaginable crushing forces. But the metal alone isn't going to cut it. The hull is reinforced with massive internal structural frames, basically like steel ribs, spaced perfectly to distribute the load. Thanks to these reinforcements, even while the ocean is actively trying to crush the sub from the outside, the internal pressure remains perfectly constant, comfortable, and safe. And finally, Section 6, Ascending to the Surface, Return to the Light. After months in the dark, surviving those crushing depths, our mission is complete. It's time to break through the waves and get back into the golden sunlight. If you remember the physics of our initial dive, surfacing is essentially that exact same mechanical process, just played in reverse. To go up, the crew activates the ship's compressed air tanks. This high-pressure air is blasted directly into the ballast tanks, violently forcing that heavy seawater out through the bottom valves. As the water is pushed out and replaced by air, the submarine rapidly becomes lighter. Once it's lighter than the surrounding displaced water, buoyancy reclaims its power. It lifts the vessel safely up through the water column until water is cascading off the hull and the crew can finally open the hatch to the open sky. I want to leave you with this final thought. This remarkable balance of physics and engineering allows submarines to explore one of Earth's most challenging environments. It really is awe-inspiring when you step back and look at the whole picture. By mastering buoyancy, sound waves, nuclear energy, and material science, we've built habitats that can literally thrive in a place completely hostile to human life. It definitely makes you wonder, if we can engineer solutions to survive the crushing depths of our own oceans, what other extreme alien environments are just waiting for us to figure out how to explore them? Thanks so much for joining me on this deep dive in today's Explainer. Keep learning, keep questioning, and I'll see you next time.